So dear students, in this video we are going to study a new relation, and that is the parallel plate capacitors. The parallel plate capacitors. Okay, so the parallel plate capacitors, by name itself, is a system of two parallel plates. Is a system of two parallel plates of cross-sectional area A each, and separated by some distance d. And one of the plate is positively charged, and another plate is negatively charged, with charge plus q and minus q, and charge density of sigma h. So this is a parallel plate capacitor. So for this capacitor, our sole intention is to find the capacitance. Our sole intention is to find the capacitance of the capacitor by simply a known formula, that is capacitance of a capacitor is charge on one of the conductor divided by potential difference V between the plates. So C is equals to Q by V. So firstly, we are going to need the value of V, and when Q is divided by that value V, we can get C. Okay, so to find V, let us consider electric field lines E directed from positive plate to negative plate. So we are going to find the value of the electric field between the plates. So let us consider the plates like this. Let this be the positively charged plate, and this be the negatively charged plate. Now, since electric field is directed from positive plate to negative plate here, so I'm going to divide this parallel plate capacitor into three regions. One, above the positively charged plate. Number two, between the plates. And number three, below the negatively charged plate. So let us find the value of the electric field at this region, one region. So here, due to positively charged plate, electric field are going towards this direction. Electric field are going towards this direction due to this positively charged plate, and due to negatively charged plate, electric fields are coming towards the negatively charged plate. Electric fields are coming towards the negatively charged plate, like this, like this, like this. That means at region 1, since here charge is minus q and here charge is q, and we know the electric field due to this type of plate, which is a good example of thin sheet. So for a thin sheet, we know electric field value was sigma divided by 2 by epsilon 0. From Gauss's law, we found the value of the electric field due to thin sheet was sigma divided by 2 epsilon 0, and we knew this electric field do not vary with distance, because there is no such thing as distance on the right hand side. That means the value of the electric field due to this negatively charged plate, which is one of the thin sheet, will be some sigma by 2 epsilon 0 here, and due to positively charged plate also it will be some sigma by 2 epsilon 0 here, because since this electric field is direction independent. So since the electric field due to positive plate is near to the positively charged plate, so it should be more. So there is nothing like that, because it do not depend on distance. That means due to negatively charged plate, due to positively charged plate, the value of the electric field will be the same, but their directions are opposite. Due to positively charged plate, the direction is towards upward direction. Due to negatively charged plate, the direction is downward direction. That means one of the electric field will be cancelled by another electric field, such that net electric field at region 1 will be 0. Similarly, at region 3, this region, the electric field due to negatively charged plate will be towards the plate, this way, towards the plate, and due to positively charged plate, this plate, at this region, the electric field will be towards this direction, away from the plate itself, this direction. That means here also one of the electric field is towards this direction, another electric field is towards this direction. So net electric field is again 0 in region 3. But in region 2, due to positively charged plate, the electric field is directed towards this direction, downward direction. And even due to negatively charged plate, the electric field is towards the plate itself. So due to positively charged plate also, the electric field is downward. Due to negatively charged plate also, the electric field is downward. That means the electric field are along the same direction. So for a charged plate, for a system of two charged plate, this way, electric field will be 0 at this region, and again electric field will be 0 at this region, but here the electric field will be along the same direction due to positive and negative charge plate. So here the electric field will have some value. So what is the value of the electric field at this region? Due to positively charged plate, electric field was sigma by 2 epsilon 0 E1, and due to negatively charged plate at this region, electric field was sigma by 2 epsilon 0, because they are independent two sheets and they are along the same direction. That means the net electric field inside the charged capacitor will be E is equals to, or direction wise they are along the same direction, so we can simply add them as scalars. So net electric field will be sigma by 2 epsilon 0 plus sigma divided by 2 epsilon 0. So it will be simply E is equals to sigma by epsilon 0. That means electric field inside the two charged plate capacitor will be E is equals to sigma by epsilon 0. Okay. Now, since we know potential difference will be equals to electric field into the distance between the charged plates. So electric field is sigma by epsilon 0. So potential difference between these two charged plates will be electric field multiplied by the distance between the plates. So it will be E into D. So it will be V is equals to sigma by epsilon 0 into D. So this will be equals to V is equals to sigma into D by epsilon 0. So this is the potential difference. Sigma into D by epsilon 0 is the potential difference between the two charged plates. Now we know capacitance is equals to, capacitance of the capacitor is Q divided by V. So it can be written as C is equals to Q divided by, our V is sigma into D by epsilon 0. Sigma into D by epsilon 0. And even this Q can be written as can be written as sigma into area. Surface charge density into area will give us the charge contained on the surface, will be equals to, here it is one sigma into D by epsilon 0. So sigma cancels. So capacitance of the parallel plate capacitor will be epsilon naught A into D. So this is the value of the capacitance of the parallel plate capacitor, and it seems to depends on the area of the plates. The more the area of the plates of the capacitor, the more the area of the plates of the capacitor, the more will be the capacitance. The less is the separation between the two plates, the lesser the value of D, the more will be the value of the capacitor. That means if area is large and if this separation is less, then the value of the capacitance will be more. So let us find some arbitrary arrangement of this plates, and let us find the value of the capacitance. Let the plate area be 1 meter square, and let distance will be 1 millimeter. So 1 millimeter will be 10 to the power minus 3 meter. Then the value of the capacitance will be epsilon 0, which is 8.85 into 10 to the power minus 12 into 1 meter square divided by 10 to the power minus 3 meter. So it comes out to be, capacitance comes out to be 8.85 into 10 to the power minus 9 farad. So this capacitance value is very, very, very small. So for a plate area of 1 meter square and for a plate separation of 1 millimeter, the value of the capacitance of the capacitor comes out to be 8.85 into 10 to the power minus 9 farad, which is very, very, very less value because it is 10 to the power minus 9. It can also be written as 8.85 into 10 to the power minus 9 farad can be written as nanofarad. Because 1 nanofarad will be 10 to the power minus 9 farad. Okay. So even this capacitance of the capacitor also depends upon the epsilon 0. What is epsilon 0 here? Epsilon 0 is the medium that separate the two plates. So here the medium that separates the two plates are vacuum whose permittivity is epsilon 0. That's why here is an epsilon 0. So the capacitance of this two parallel plate capacitor depends upon the area, the separation between the plates, and also the medium between the two plates, or medium that separates the two plates. So in this case it is vacuum, so here it is epsilon 0. Now since the value of the capacitance here is 1 nanofarad, for a normal arrangement of 1 meter square plate and separation 1 millimeter, capacitance come out to be very small. So that's why 1 farad is very large unit. That's why 1 farad is very large unit. Why it is large unit? Because for the separation of 1 meter square and for an area of 1 meter square and separation of 1 millimeter, still the capacitance is very small. Okay, so let us see when the capacitance value is 1 farad, then what should be the area of the plates? That we'll calculate, and we will see the largeness of the unit 1 farad. So let us take capacitance of some capacitor is 1 farad. Epsilon 0 is 8.85 into 10 to the power minus 12, and we are going to find area divided by, let us take separation to be 1 millimeter itself, 10 to the minus 3 meter. So it comes out to be area is equals to 10 to the power minus 3 divided by 8.85 into 10 to the power minus 12. So it comes out to be approximately 10 to the power 9 meters square. Okay, that means to have a capacitance of 1 farad for an arrangement of two parallel plate capacitor, the area of plate should be equals to 10 to the power 9 meters square. That means one of the plate area or length into breadth of the plate must be equal to 10 to the power 9. Shows that 10 to the power 9. So what is this actually? What is this value? If we convert this into kilometer, then it comes, okay, roughly it comes out to be length to be 30 kilometer and breadth to be 30 kilometer. So if you have a parallel plate capacitor, and if you want to make the capacitance of that parallel plate capacitor to be 1 farad, then your plate area must be equals to 30 kilometer in length and 30 kilometer in breadth. That's why 1 farad is very large unit. So we will deal with very small units like nanofarad, microfarad. 1 microfarad is 10 to the power minus 6 farad. 1 millifarad is 10 to the power minus 3 farad. 1 nanofarad. So we will deal with this type of unit, since 1 farad is very large unit. So this much for today. We're going to continue with our discussion in the next class.